Welcome to this fifth session in a series of masterclasses hosted by 2DPLOY, with focus on greenhouse gas calculations and data requirements. Hello, my name is Ilse Morgens. I work at Vito on Climate and Energy Policy. In the 2DPLOY project, I focus on avoided greenhouse gas emissions. I've been working with the methodology for several years now and have seen it evolve, becoming clearer over time, though still quite challenging for complex or hybrid projects. Before we start, a couple of words on the 2DPLOY project. The 2DPLOY project is a European funded project. It's a CSA, Coordination and Support Action type of project, where we look at the Innovation Fund and our main goal is to bring more successful projects to the goal. The goal of the project is to develop an innovation pipeline to facilitate and promote funding proposals for deployment of low-carbon technologies. On the right in this slide, the project partners are listed. The project is led by SINTEF. We cooperate with the other four CSA. As 2DPLOY, we focus on low-carbon technologies in energy-intensive industries, whereas LEADS focus on carbon capture, use and storage, and REALIZE and Diamonds for IF on renewable energy generation, and H2IF on energy storage and hydrogen. The main objectives of Deploy are: first, to establish a continuous innovation pipeline for low-carbon technologies within energy-intensive industries. Second, to develop best practices and support pilot innovation fund proposals. Third, feed the 2DPLOY innovation pipeline and share learnings with priority stakeholders. Fourth and last, foster open collaboration and create synergies. The pipeline consists of a self-check matrix. This is an online questionnaire built around the award criteria, and it gives you a first idea of whether your project that you are submitting is mature or not. Second, an expert interview where we go over the questionnaire with an expert in more detail and make sure there are no misunderstandings. Then the project passes through the evaluation commission that consists of experts who would then do a more deep dive into the different award criteria and check whether your project is mature enough to prepare a proposal for submission. Support with the application is provided for those projects that are really mature and are ready for the Innovation Fund. We will not write your proposal, but give feedback based on the text that you already have, or the greenhouse gas calculations that you did, for example. If at some point you need to leave this pipeline because, for instance, your project is not yet mature enough, we have foreseen also advice and feedback on potential other funding opportunities. For developing the master classes, we followed the next steps. First, we evaluated the materials available from CINEA. Second, we analyzed lessons learned from previous calls. And finally, we interviewed several key stakeholders to listen what are the issues they struggle with. This way, we can provide targeted support for Innovation Fund proposals. To address the challenges, we offer an advanced masterclass consisting of 6 lectures linked to the award criteria. Each session tackles common weaknesses or challenges. We provide practical guidance to help applicants meet the requirements with more confidence. We will focus on the material that is already available from CINEA to make sure it is used more effectively. This slide gives the overview of the masterclass and its 6 lectures. Okay, That was a short introduction of the project, and we now start with the lecture on the greenhouse gas calculations. Let me briefly walk you through what we will cover. We'll start by positioning this work in relation to the guidance and documentation provided by CINEA. This ensures alignment with their expectations and methodological framework. Next, I'll explain why robust greenhouse gas calculations are essential, not just for reporting purposes, but for credibility, comparability, and demonstrating real impact. Then we'll look at how to quantify emission avoidance. I'll outline the general approach, key steps, and methodological logic behind the calculations. Finally, I'll highlight the main assumptions and data sources used. Transparency here is critical, since assumptions strongly influence results and interpretation. With this structure, we move from context and rationale to methodology and transparency. In this part, I provide you with useful references to CINEA materials, including links to the website. This lecture is based on these references. First of all, the methodology document. The last version today is of 15th of January of this year. It is the official and required reference for greenhouse gas emission avoidance calculations under the Innovation Fund. It is the authoritative reference, the Bible for greenhouse gas calculations. Pay attention may change with each version as the Commission refines assumptions and clarifies treatment of new sectors. The greenhouse gas calculator is an Excel file and is available on the official call page under Application Form and Templates via the EU Funding and Tenders portal. The calculator can be found in the section Topic Conditions and Documents under Application Form and Templates. Please ensure that the full section is displayed by clicking on Show More, see in the picture here. The calculator is provided for information purposes only. For submission, you need to use the forms available in the submission system under Part B templates. On this page, you can find videos explaining the greenhouse gas methodology and calculation approach. Scroll down to the tutorial section, see figure on the left. The videos relevant for energy-intensive industries and carbon capture, utilization, storage are indicated in red. In this slide, you find links to example calculation sheets for specific project examples in the energy-intensive industries, like there are the production of e-fuels, production of green hydrogen with data traceability, the production of methanol, direct air capture with CO2 storage, and manufacturing of electrolyzer stacks. And this CINEA presentation contains best practices, do's and don'ts, and highlights the main mistakes related to greenhouse gas emissions avoidance. Refer in particular to slide 8 to 17 for do's and don'ts. And note that the presentation is not fully aligned with the current methodology anymore. Nevertheless, it still contains relevant and useful information. We will return to this at the end of the presentation. And now we move over to the importance of the greenhouse gas calculations reflected in the award criteria. The greenhouse gas methodology is the basis for assessing a project's potential to avoid greenhouse gas emissions. It helps applicants estimate avoided emissions over the first 10 years of operation and consists of two main calculations, the net, absolute, and the relative greenhouse gas emission avoidance. We'll discuss these further in the section on the calculations. And this slide highlights the importance of the greenhouse gas calculations in the application. Nearly 1/3 of the total score depends on them. In the 2025 call, the greenhouse gas related award criteria include absolute greenhouse gas emission avoidance for 2 points, and this is scored against the median of all proposals. Relative greenhouse gas emission avoidance for 5 points, ranging from 0 points for 0% relative avoidance up to 5 points for 100% relative avoidance or more. There is a threshold of at least 75% savings for pilot projects and at least 50% for other projects. Another 5 points are awarded for the quality of the calculation, which must meet minimum requirements. such as emissions below the ETS benchmark. For bioeconomy projects, the biomass used must meet the sustainability requirements of the Renewable Energy Directive. And new is the TNSH principle, do not significant harm. A project must not cause significant harm to any of the EU's 6 environmental objectives, as defined in the EU taxonomy regulation. Applicants must provide a structured TNSH assessment explaining how potential risks are identified and mitigated. If the quality or reliability of the calculation is weak, or if the methodology is applied incorrectly, points are reduced, and in serious cases the proposal can be rejected. In total, these criteria add up to 12 points, plus 1 bonus point, 1 for potential net carbon removals. Cost efficiency is another key criterion, worth 12 points, and it's closely linked to greenhouse gas emissions avoidance. It's calculated as the requested grant divided by the absolute greenhouse gas emissions avoided. Applicants can request up to 60% of eligible costs, but asking for less increases the efficiency score. For most projects, if the cost is below 200 euros per ton, the score is 12, minus 12 times the cost ratio divided by 200. For pilot projects, the threshold is 2,000 euro per ton. While scoring weights differ between project types, such as large-scale pilots or clean tech manufacturing, the greenhouse gas and cost efficiency criteria remain the same for all. And up to 3 additional points are awarded for qualitative aspects, such as clarity, transparency, robustness of the cost calculation, justification of data, and compliance with Innovation Fund methodological standards. In the next section of this lecture, we discuss calculating the greenhouse gas emission avoidance. We go briefly through a recap of the methodology based on the official methodology document and the available tutorial materials here on the slide. The methodology includes 2 key formulas: the net absolute greenhouse gas emission avoidance, which is the difference between emissions in the reference scenario without the project and those in the project scenario. The relative greenhouse gas emissions avoidance, calculated by dividing the absolute avoidance by the reference emissions over a 10-year period. The relative greenhouse gas avoidance can never be negative. If the absolute avoidance is 0 or negative, it is set to 0. In rare cases where reference emissions are 0 or negative, but the project still achieves positive avoidance, such as direct air capture, capture of naturally released CO2, or CO2 capture from existing bioenergy plants, the relative avoidance is set to 100%. For hybrid projects, all components should be combined carefully, with clear system boundaries for each part. Reference and project emissions from different sections of the methodology must be added together, avoiding any double counting. Finally, all projects must meet the minimum requirement for relative greenhouse gas emission avoidance as defined in the call text. See also the previous slide on the award criteria. And these are the process steps of the greenhouse gas emission avoidance calculation. The first step is to clearly understand the project, what practice or product it aims to replace. Does it involve a change in the process or a replacement of the final product? The principal product should reflect the main aim and innovation of the project. And who are the main parties involved in its implementation? It's crucial to define the project scope clearly and to carefully check the eligibility conditions in the call text for the specific topics. For example, a project might focus on producing an innovative fuel for transport application. Another might aim to use an alternative fuel in an innovative vessel or aircraft, or even combine both production and use. We will look in some examples into more detail on the next slides. The first example, consisting of 1A, B, and C, is on production and/or use of hydrogen. In the first example here on the slide, the project focuses only on producing hydrogen for transport applications in navigation, replacing fossil fuels. Since it targets production only, it falls entirely under the energy-intensive industries category. In the second case, 1B, the project covers both production and consumption of hydrogen in navigation. Such hybrid projects must combine all relevant components and clearly define the system boundaries for each. The greenhouse gas emissions from each part are then added together, avoid the double counting. This type of project falls under both energy-intensive industries and mobility. In this third example, the project focuses only on the use of hydrogen as an alternative to fossil fuels. This is classified under mobility and follows the corresponding methodology. To conclude this example, in general, projects that only produce fuels for transport applications should apply under energy-intensive industries. However, projects that include both production and use, for example, producing hydrogen and using it in a vessel or aircraft, may apply as hybrid projects, combining energy-intensive industries for production and mobility for use. In such hybrid projects, any CO2, methane, or N2O emissions avoided by replacing fossil fuels must be counted in the energy-intensive industries reference scenario and excluded from the mobility part to prevent double counting. Mobility projects in aviation and maritime sectors may also claim additional benefits, such as reduced non-CO2 climate impacts like black carbon. And here's another example, 2, consisting of 2A and B. 2A, a project producing hydrogen using an on-site wind farm. The main product is hydrogen, but during wind peaks, part of the electricity is exported to the grid. In that case, the project can be submitted as a hybrid, with an energy-intensive industries part for hydrogen and the rest part for wind energy. Only the exported electricity is included in the rest calculation. If all the renewable electricity is used for hydrogen production, the project follows only the energy-intensive industries methodology and is not considered hybrid. In a hybrid project, the applicant must show that the renewable power is primarily used on-site for hydrogen production, with only the surplus exported. In 2B, alternatively, if a renewable plant supplies all its power to the grid, but happens to be co-located with an industrial installation, say a factory producing bio-based packaging to replace polystyrene, then it should apply as two separate projects, one under RES for power generation and one under energy-intensive industries for the product. A hybrid application wouldn't apply in that case. Next, the applicant needs to identify the category and sector their project falls under. Each project should be classified according to its principal product, the main aim of the project. Getting this definition right is essential, as it determines the correct sector and category for the application. For energy-intensive industries, this means the following. Principal product should replace a product whose conventional production is covered under Annex 1 of the EU ETS Directive. Once the classification is clear, applicants can use Table 1.1 in the methodology document to see which sections apply to their project, alongside the general guidance in Section 1. Each section provides instructions, provisions, and ready-to-use equations for calculating greenhouse gas emissions avoidance. Keep in mind that some projects may have more than one principal product, or may fall under more than one category. These are considered hybrid projects. Projects that produce a CCU product can include this as one of their principal products. Other Innovative processes using biomass feedstock to produce bio-based materials or biofuels in biorefineries are also included. Bioelectricity and bioheat, however, fall under the renewable energy sources category. The methodology is linked to the sector the producing entity belongs to. This slide shows examples of sectors covered by Annex 1 of the EU ETS Directive. For the full list, you should check the methodology document. Other possible products include electricity generation and carbon capture, utilization or storage. In such cases, you can apply under Other, with the product defined as CO2 transport or CO2 storage. When a project combines activities from more than one category, like energy-intensive industries, renewable energy sources, energy storage, or mobility, it's considered a hybrid project. In that case, the applicant still needs to choose one main sector and principal product that best reflect the project's main aim. Hybrid projects must define clear system boundaries for each component, calculate emissions for each part, and then sum them up, removing any double counting. Reference and project emissions are calculated for each section of the methodology and then combined to determine total absolute and relative greenhouse gas avoidance. Since only one spreadsheet can be uploaded, applicants must merge the relevant greenhouse gas calculators, for example, adding REST tabs into the Energy Efficiency Industries calculator, and complete the common tabs once for the full project. Next, you need to understand the emissions and the boundaries of the greenhouse gas calculations. For energy-intensive industries projects, the methodology follows life cycle stages. The reference scenario represents what would happen without the project, while the principal product reflects the main innovation. Applicants should provide a detailed process diagram for both scenarios, showing all sub-processes, inputs, products, and relevant energy and material flows. Emissions must cover all sources, from inputs and processes to use phase changes and end of life. The system boundary for the greenhouse gas calculation must cover all relevant processes, including the innovative practices, their downstream steps, and, where applicable, upstream processes, only if they are under the applicant's control. It can span several physical locations. Transport emissions are generally excluded, except for CO2 transport in CCU or CCS, product distribution when it differs from the conventional one, and biomass or waste transported over 500 kilometers. The calculation must also include material and energy inputs, change to in-use, and end-of-life emissions. Next step is to identify the reference scenario for your project. Establishing the reference scenario correctly is essential, as it forms the basis for calculating avoided emissions. The reference represents conventional production of an equivalent quantity of the principal products. If the new product is physically similar, we use the same quantity. If it's different, we calculate the equivalent function. For example, hydrogen for fuel cell vehicles is adjusted using an energy efficiency ratio. There are 9 possible reference cases, and projects with multiple co-principal products may need to combine several reference scenarios. When defining the reference scenario, first check whether an EU ETS product benchmark applies. If so, include all emissions that the benchmark doesn't cover, such as inputs, non-principal products, combustion, and end of life. Benchmark values for refinery units and processes included in Annex 2 of the Commission Delegated Regulation shall not be used to set reference scenario emissions. If no single benchmark fits, you can combine EU ETS product and sub-installation benchmarks to construct a suitable reference scenario. For example, combining the benchmark for a slightly different product with the benchmark for additional heat and fuel use. Or, in case of steel production, combining the benchmark for coke production with the hot metal production benchmark to produce the full reference scenario. For modifications to existing installations, projects adding carbon capture units are considered modifications. But if the investment exceeds 1/3 of a new facility's cost, or if only inputs change, it's not treated as such. For transport and fuel substitutes, use fossil fuel comparators, and for natural gas substitutes, calculate based on equivalent energy content and the standard emission factor. When the principal product is synthesized from natural gas and the life cycle emission value available in data hierarchy, ensure emission factors are based on a process with natural gas as the main feedstock. For cases like direct air capture or CO2 storage and transport, specific rules apply and can be found in the methodology. We not discuss those here. And finally, when proposing your own reference scenario, make sure it reflects the same function or quantity as the principal product, with all assumptions and calculations clearly justified. Now let's have a look at how to complete the greenhouse gas calculators. Inputs include all material and energy entering the system from outside its boundary, such as heat, electricity, chemicals, feedstock, and biomass. Fossil fuels used within the system are handled separately under processes or end of life. Some minor inputs can be disregarded as de minimis. This has to be justified in your application by e.g. an emission factor from literature or showing with examples that emissions are below a certain level. When addressing waste inputs, we assess the changes compared to the existing disposal route. This includes considering whether the waste would otherwise be recycled, landfilled, or incinerated, with or without energy recovery. Other emission factors may be selected in line with the input data hierarchy. See Appendix 1 of the methodology. When doing so, you must be sure that the choice of emission factor is clearly justified, that EU ETS benchmarks values are not used for inputs, and that adjustments are made where necessary to exclude carbon content and to avoid double counting. Also note that applicants are no longer permitted to apply the 15% upstream adjustment. This has been removed since the 24 call. Process emissions must include the following elements within the system boundary: CO2 from fuel combustion, other greenhouse gas emissions including CO2, methane, and N2O, transport emissions must be included where relevant, for example, CO2 transport in CCU, CCS projects, transport of products when delivered in a different form, transport of biomass or waste over distances exceeding 500 kilometers. In addition, changes in emissions from waste processing must be accounted for. Note that emission savings from timed operation in electricity-consuming projects are no longer considered under process emissions. Electricity from virtual storage should be treated as a product. In such cases, the project must apply as a hybrid project. For principal products that contain carbon atoms, the fate of those atoms should be considered. If the product is combusted during use, like fuels, emissions from principal product combustion must be included, and the associated CO2 emissions should be accounted for. If the product is not combusted, end-of-life emissions must be assessed. If the carbon is recycled into new products, no end-of-life emissions are accounted for. If the carbon is incorporated into a material, and for a storage period of more than 50 years, 50% of the contained carbon is considered emitted. Otherwise, 100% of the contained carbon is considered emitted. Any non-CO2 greenhouse gas emissions occurring at end of life must also be included. Additional reductions in end-of-life emissions may be accounted for as negative emissions. It is credits where they are duly justified. And on end of life, a separate lecture number 6, is foreseen. The methodology covers all greenhouse gases listed under the EU ETS. That's CO2, methane, N2O, HFCs, PFCs, and SF6. It focuses on capturing the most significant emissions within the system boundary. For example, non-CO2 emissions from combustion, end-of-life emissions of non-CO2 gases, and non-CO2 greenhouse gases released from chemical processes, such as refrigerant manufacturing. Certain emissions are excluded from the calculation of absolute and relative greenhouse gas emissions avoidance unless otherwise specified. This includes emissions from capital goods and construction, and from fossil fuel extraction, processing and distribution, for comparability with the EU ETS benchmarks, which considers only combustion emissions of fossil fuels. Fugitive emissions from geothermal well testing or bleeding are also excluded, as well as avoided methane from alternative disposal of biomass, and ILUC emissions from crops and carbon depth in forestry. Emissions linked to decommissioning, employee commuting are not included either. The same applies to manufacturing emissions for component production and transport of raw materials or intermediate products within the system boundary. Calculators have been made available to enable the calculation to be documented in a consistent way. It is important to use these calculators. These include the default parameters that will be deemed as constant throughout the duration of the project. For example, ETS benchmarks, to secure alignment and reduce the volume of data to be defined and monitored by the applicant. Hybrid projects require combining of greenhouse gas calculators into a single Excel file. Applicants need to transfer the TAPS reference emissions, project emissions, and conversion factors from each relevant calculator and remove double counting of emissions or removals. The Assumptions tab is the place to document all your assumptions, both quantitative and qualitative. Fill in all relevant columns like unit, description, basis or source, including links if available. When preparing your calculations, make sure to document all quantitative and qualitative assumptions clearly. Assure transparent documentation. That means explaining the methods and data you used to estimate or extrapolate operational values, so reviewers can easily assess how robust your data really is. Use the Assumptions tab for this. Describe each assumption clearly, explain the basis for it, ideally using conservative assumptions, so you don't risk overestimating outcomes. If you have information on uncertainties, include that too, and indicate how those uncertainties are treated. And whenever possible, link to your original data source. If a direct link isn't available, give full details such as the title, author, or the contact person. Avoid embedding assumptions directly as hard values in your calculation formulas. Instead, refer to the assumptions listed in the assumption sheet. And don't scatter assumptions throughout your document. Keeping them centralized in one place makes the evaluation much easier and faster. For the project-specific data used in greenhouse gas avoidance calculation, a monitoring plan consisting of a detailed, complete, and transparent documentation of the information and data sources shall be submitted at the application. When filling in the monitoring plan, use the extra columns for data traceability to clearly describe how data is gathered, how it is checked internally, and who validates it. Also specify where the data will be stored. This ensures transparency and accountability. These steps don't just help create a clear verification trail, they also lay the foundation for future monitoring plans for projects that are awarded funding. And the last step is to upload the calculators to the portal. In the calculators, the indicators are calculated automatically and shown in the Summary tab. Check if these are reasonable and then simply transfer these values to the mandatory forms as part of your application. We will now move to important assumptions and data sources for greenhouse gas calculations and further highlight the key elements that require particular attention. When preparing your greenhouse gas emissions avoidance calculations, it's essential to use the most precise assumptions available for your activity data, operational performance, and resulting greenhouse gas emissions. Make sure your results reflect the best realistic estimate of expected emission avoidance, not an overly optimistic one. Accuracy and credibility are key. Keep everything consistent with the rest of your proposal and justify all assumptions with verifiable references or reliable data sources. And finally, always respect the hierarchy of sources. Prioritize primary, high-quality data wherever possible. This strengthens both the robustness and credibility of your application. When you need greenhouse gas emission intensity or combustion emission values that aren't provided in the methodology, you should take them from the approved hierarchy of data sources. These emission factors must represent typical real-world values for each input or product. When we talk about the hierarchy of sources for inputs and products in industrial projects, including projects with CCS, we're referring to the order of reliability from the most authoritative to the least reviewed data sources. You should preferably use data from sources as high as possible in the hierarchy. If you use a lower level source, you must clearly justify why it gives a more representative value. You can't adjust official values to reflect your own supplier situation or to match a zero-emission electricity assumption. Keep in mind that values for heat, electricity, and hydrogen are already given in the methodology, so never take those from external sources. Also, EU ETS benchmark values can't be used here for inputs or products, since they don't match the required scope. As already said, you should always use data from the highest possible level in the hierarchy. And finally, if you're using data from multiple sources at the same level, you need to explain why. Selective cherry picking of convenient values is not allowed. At the top of the hierarchy, we have official and regulatory references, like the RED II annexes for bio-based emissions and the IPCC guidelines, which define combustion and emissions data. These are the gold standard for consistency and credibility. Next, we have two JRC reports holding interesting information. One of 2019 on definition of input data to assess greenhouse gas default emissions from biofuels. It contains emissions intensity for most widely used process chemicals in Table 47. Second of 2020, the GEC well-to-tank report offers coherent, reviewed datasets for various inputs and products. Then we move to reviewed data sources, which are reliable but not always regulatory, such as EcoInvent or equivalent programs Gabi OpenLCA. For these, use the cutoff system model, and when allocating emissions across products, use economic value as the allocation basis. Other official sources like IPCC and IEA, and other reviewed sources like E3 and the GMIS databases. And we also have peer-reviewed studies in this category. When you use data from external sources, make sure you properly reference it so evaluators can verify it. But you don't need to review or justify the full methodology behind that source. However, LCA-based values can only be used when they follow the hierarchy of data sources. And remember, it's not acceptable to just copy a value from literature. You still need to develop your greenhouse gas emission avoidance calculations fully in line with the required methodology. Below in the hierarchy are own estimates, which are acceptable if they are clearly documented and justified. And finally, at the bottom of the hierarchy is gray literature, things like commercial reports or websites. These can be used only when no better data is available, and they should always be treated with caution. During project execution, it's important to monitor and report all key assumptions. They don't end once the application is submitted. The monitoring plan should include the project-specific assumptions. If during implementation the actual operation differs from what was assumed, this can have serious implications. It could directly affect your greenhouse gas avoidance claims or even the grant disbursement. So, regular tracking and accurate and transparent reporting of assumptions in the application already are essential to maintain credibility and compliance throughout the project. All measurements need to be taken using calibrated equipment in line with industry standards and the EU ETS MRV requirements. This ensures that all data used in your calculations are accurate and verifiable. In the data traceability section of the greenhouse gas calculator, make sure to clearly describe which area or department is responsible for collecting and archiving the data, the data sources and monitoring equipment used, including their accuracy and calibration details, the monitoring frequency and QA/QC procedures, and finally, a brief description of the methods used and the reliability of the data. This provides transparency and helps ensure that your project's monitoring process can be easily reviewed and validated. When it comes to monitoring and reporting, there are several key parameters that every project must include at a minimum. First, the quantities of all inputs used by the project, and it's important to clearly identify which ones are major and which are de minimis. Next, the outputs, means both main products and any byproducts or non-principal products. You also need to record the amount of fuels consumed to provide energy for your processes. Then the emissions of greenhouse gases associated with project operation. These can be directly measured or calculated from other monitored parameters. Include the emission factors for any biomass-derived inputs and document the origin of hydrogen if it's used in the project. And finally, for projects using biomass-derived fuels or materials, make sure to monitor the origin and type of each batch, demonstrate that it meets sustainability requirements, and report the associated emission factors according to the RED calculation rules. Some parameters are considered constant for the entire duration of the project, unless specifically stated otherwise. You can find the full list of these parameters in Table 5.2 of the methodology. This means that once defined, these values don't need to be updated or monitored continuously. They remain fixed throughout the project period. These are, for example, conversion factors, greenhouse gas emission factors of fuels. Emission factors are on a net calorific value basis and have been rounded to the fourth decimal. Now, let's look at some common problem areas and how to handle them effectively. First, make sure all data sources are well justified and clearly referenced. Use robust operational data and document all assumptions transparently. Avoid using overly aggregated data. Always present details in a disaggregated and traceable way. When facing uncertainty, use conservative values and be careful to avoid double counting, especially in hybrid projects. Clearly define your system boundaries and the principal products before selecting the right sector, category, and calculator. Follow the Innovation Fund methodology closely and allow time for checks and revisions to avoid formula or application errors. So start in time. Use credible real-world data from pilots or operational sites and set up a solid monitoring plan that defines how data will be collected and verified. Also include time-related effects like learning curves, degradation, and ramp-up phases. Finally, make sure your work is transparent and reproducible. Provide clear references and links to your data sources so that results can be easily verified. To conclude, we would like to recall the best practices that remain relevant from the 2024 call. The reference to the corresponding presentation is included at the start of this lecture and also here. This slide summarizes the most common mistakes observed in greenhouse gas emission avoidance calculations from the 2024 call. First, emissions that are not covered by the methodology are sometimes included, or conversely, emissions that should be covered are excluded. It is essential to strictly follow the methodological scope. Second, assumptions and data are not always supported by adequate evidence. All key assumptions must be transparent, justified, and documented. Third, we often see an incorrect choice of reference scenario or inappropriate emission factors. The reference scenario must reflect the most credible and compliant alternative. Fourth, there can be inconsistencies in scope between the reference and the project scenario. Both scenarios must be fully aligned in terms of system boundaries and methodological approach. And fifth, incorrect project boundaries are sometimes applied, deviating from the methodology. The defined system boundaries must be respected. We will now look at some practical tips for energy-intensive industries projects, covering the full change from inputs to end of life. First, make sure to complete all sections of the greenhouse gas calculator, from inputs to processes and finally to end of life. Omissions often lead to inconsistencies. Inputs must always be included, even if they are identical in both the project and the reference scenario. Transparency and completeness are essential. Any de minimis inputs should be clearly justified. Emissions related to upstream fossil fuel supply, such as extraction, must not be included, as they fall outside the scope of the methodology. Note that combustion emissions for fuels are no longer treated separately in the EF25 call. They are now accounted for under end-of-life emissions. Finally, ensure that end-of-life emissions are included for chemicals and other carbon-containing products where relevant. Finally, we look at practical tips concerning project assumptions, in particular the use of principal products. The intended use of the product must be clearly substantiated and justified, for example, through draft contracts or other supporting evidence. For products that can be used either as chemicals or as fuels, the reference scenario must be aligned with the intended use. This means building it on the relevant benchmark or on the appropriate fossil fuel comparator, depending on how the product will be used. If the final use of the product is not yet defined, conservative assumptions must be applied in the greenhouse gas emission avoidance calculation. If the assumed use of the product is not well substantiated, this may be flagged as an issue during evaluation. Likewise, if less conservative assumptions are used, this may create difficulties later during monitoring and reporting of greenhouse gas emission avoidance. Thank you very much for your attention. We hope this overview has helped clarify the key methodological elements and the main pitfalls to avoid when preparing your application. Should you have any questions after watching this recording, please do not hesitate to contact us. We wish you every success with your application.